Right. Questions on the homework?
Number 33.
Number girl, what's number 33? What is number 33?
Hang on, I will read it to you. There.
Yeah. What is it? Yeah. Oh, Samuel probably has the textbook.
Yeah,
Is it?
Oh, not in that textbook. In the other one, here.
this one.
The blue one.
Oh, what does it look like in the
Yes.
Here it is.
This edition.
Show that vector orth A equals B minus projection A on B.
want to show that orth equals B minus the projection of B onto A is orthogonal to A.
Sounds like it.
Okay.
Can you first explain the question? Because I don't quite understand it.
Okay, what does the word orthogonal mean? We talked about that last
Right
time.
angle.
Perpendicular, but in more than 2 dimensions, right? So basically they're saying there's this vector that they call the orth vector, and it's defined by this, right? So this is actually a vector, right? Because the projection is a vector, and this is a vector. You subtract 2 vectors, you get another vector. So this is just the definition of a vector that they're giving this name. Now they're saying, prove that that vector is perpendicular to the vector A. How do you know if 2 vectors are perpendicular?
Their cross product is 0.
Dot product is
Dot
0,
product.
right? We didn't even do cross product yet. So all you have to do is show that if you dot product this with that, you always get 0. What is this though?
That's A dot B over absolute A. No, that's it.
Squared times the vector A, right? So that's the definition of the projection. So we want to show that if you take B minus A dot B over the magnitude of A squared times A, and you dot product that with the vector A, the answer will be 0, because that would mean they're orthogonal. Right? So that's a very simple criterion to know if 2 vectors are orthogonal. So that's what we're going to do. But now we have the properties of the dot product says you can actually distribute across sums, right? So that's what we're going to do. So now I can dot product this with that. This is B dot A, right? Minus, now I'm going to dot product this with that. This is A dot B over A squared, right? Times A dot A, right? Does that even make sense? Why does it make sense?
Because A dot A.
The multiplication here is what? It's not a vector multiplication. That's a scalar multiplication, right? That's a dot product. Does it make sense to do this? What kind of quantity is this? It's a scalar. A dot B is a scalar. You're dividing by a magnitude. That's also a scalar. So this is just a scalar. It's a constant, right? It's just a number. It's not a vector. And I can take a scalar and multiply it by a vector, right? This is called scalar multiplication. We defined that last time. So this is just another vector, right? And then I'm dot producting it with another vector. So this makes sense. It actually makes sense for me to do this operation. What do we know about A dot A?
It's equal to the magnitude.
It's equal to the magnitude of A squared. So this is just the magnitude of A squared, which just cancels with that. And so we have B dot A minus A dot B. And what's that? That's 0 because these are equal, right? Dot product is commutative. Therefore, those 2 vectors are orthogonal. Other questions?
35 from the first edition.
Right, from your book. Let's see what 35 says. Use scalar projection to show that the distance from a point to a line is that. Okay. So I guess start by drawing a picture, see what's going on. Right? Let's this be my line, right? So this is the line ax plus by plus c equals 0. Random point here. And of course when they talk about distance, they mean perpendicular distance, right?
Yeah.
So basically, that's the distance I want to find, right? We want to show that D is equal to magnitude of AX1 plus BY1 plus C all over the radical A squared plus B squared. Okay, ideas. They said use scalar projection. So I'm thinking what we want to do is project some vector onto this, make sure it's that length, and then we can find it that way. Let's have a vector from the line going to that point. Let's say it goes from the point x, y. Okay. All right, so now since we need scalar projections and stuff like that, we need to know what these vectors are, right? What is the vector that gives me the direction of this line?
Oh, okay. Yeah, okay.
Okay. So what is the vector here?
Well, okay, no, maybe one of the endpoints is going to be P1.
This is P1, I think.
We know that, and I thought I had it inside, but I don't think I did.
So what I can do is I'm going to call this vector the D vector. Really, I want to find its magnitude. I can call this one, what do you want to call it? U. Okay, so really what do I want? I want the scalar projection of U onto D. Basically, I want to find the magnitude of that. Right, that's basically what I want to find. This could be negative, so let's find the magnitude of that. That's basically what we want to find. That will actually help us answer our problems. But we need to know what the vectors are that we're using. How do I find the vector for this, the direction of this line?
I would do rise over run, but I'm...
Okay, so rise
because
over
rise
run.
over run would give you x over y, y over
Y over
x,
x, yeah.
and that would
The
give
y
you
component over the x
your
component.
I hat.
Okay, how do I
and your
get
j
to rise
hat.
over run?
Well, it used to be y equals mx plus b, but I see a c in there, so I'm lost.
Wait, why don't we just do the x1 minus x and then...
But you're on the right track.
Negative A over B.
We like it y equals mx plus b. Let's try to write it in that form. How do I write this line in that form? Solve for y. What do I get?
Y equals negative ax negative c over b.
There's your rise over run right there.
Oh,
Right?
sweet.
Y equals mx plus b. Now, we're big kids. You don't have to call it b. It could be any letters. These are just dummy variables after all. Right? There's my rise over my run. So I can actually describe this vector by something like b minus a. Right? Or minus ba. That's fine also. Right? But guess what? If I know that line, I actually know what D is as well, right? We did
Right.
this. What is the general vector that is perpendicular to a vector that looks like this? Switch the components, change the sign on one of them, right? That's the vector AB. What's this vector?
The A squared plus B squared equals C squared.
Hmm?
AB dotted with the vector P1 minus the arbitrary point.
Yeah, find these points. Final point, initial point. We can actually find the vector from this. This would be the vector x1 minus x, comma, y1 minus y. So now we know all the vectors. What I want to do, I want to project this vector onto that one. So let's do that. Of u onto d. And what's that definition?
It's going to be the dot product divided by the length of A.
The length of what?
Well, not of A.
Absolute
Of
U.
D.
Of d.
B.
Yeah.
Okay. What's the absolute value of d? D is just the vector AB. It's the square root of a squared plus b squared, right? Ah, looking promising. What is the dot product of u and b?
AX1 minus AX plus AY1 minus AY. Yeah, B. Yeah.
Okay, and this is in absolute values because that could be negative. And so this is ax1 minus ax plus by1 minus by. Start to simplify this. What do they have over here? ax1 plus by1. And we have ax and by. And minus ax plus by is actually equal to c. Done.
What is the D?
The d was the distance here. So d is really just the magnitude of this scalar projection onto that vector. Okay. And part B of that question, once you have the formula, then that's obviously just part of the points. So then for the part where it says, you know, the distance of the point minus 2 comma 3 to the line 3x minus 4y plus 5. Yeah, so you're just going to plug in x1, y1 would be minus 2, 3, a would be 3, and b would be minus 4. You just plug into this formula and compute the values. Any other questions? Yeah.
23.
The first edition or second edition?
Second.
What does that say?
Finding unit vector that is perpendicular to both vector I plus vector j. And
Okay.
Ah, that's nice. You know why that's nice? Because in the very next section we're going to find a really nice way to do something like that. Like in general. Like finding a vector that's perpendicular to two other given vectors. I can get rid of this?
Yeah.
So that question was from the first edition. Here we're in the second edition, 23. I want a vector ortho to both. What was the vectors?
I plus j and I plus k.
Yeah, I don't particularly like this notation. So this is 1, 1, 0, and this is 1, 0, 1. Okay? I need to find a vector that's perpendicular to both of those. How do I get it? Yeah.
Well, what I did, I put them both equal to 0. Well, actually, I did the 110 dot u equals 101 dot u equals 0, and then.
Okay, so you call this,
Yeah, like.
let's call it V for now, because I
Okay,
don't
so-
think you'll end up with a unit vector right away. So you said 110 dot product with this V
Yeah.
it should be equal to 101 dot product with that V. The answer should be 0. Okay?
Correct.
Yeah, that's what we
And
want.
then just kind of thought about it, and I made the other vector negative 111, and just kind of put that one. Negative 11.
You just put negative 1, 1, 1.
Yeah.
Okay, so that would give you 0 here, and
That would give you 0 there.
that would give you 0 there. Okay, let's say someone couldn't find that right away. How would you approach it?
I said the vector is x, y, 0, and do the dot product with each other.
Yeah, x, y, z. That's fine. Yeah, your answer so far was okay, but I wanted the answer for someone who didn't just see it. How would they approach it? Right, just make the vector a general vector, right, and then try to figure it out from the equations. So this is going to give you the equation what? X plus y
Plus y
equals
equals 0.
0.
And that one,
This one is going to give you
x plus v,
x plus z equals 0.
Which is
x equals negative y, and x equals negative 0.
Right, so x equals minus y, and x also equals minus z, right? So that tells you, what does that tell you?
The relationship.
This means that y must be equal to z, right? Because they're both equal to x. So you know, whatever vector you pick, you want the y component and the z component to be the same number. And then the x just has to be the negative of whatever number you pick, right? So we can start with easy ones. Let's say they're 1. Say y equals z equals 1. This means x equals minus 1. This means your v would be minus 1, 1, 1, which is the vector that he came up with, right? And any numbers we picked here would work. That's fine. Why? Because we're going to have to find the unit vector. We're going to divide it by its magnitude anyway. We'll end up scaling it to the same guy. Or the negative of this guy could also work, right? I could have 1, negative 1, negative 1. Right? So this means that the unit vector, because we want the unit vector, is just going to be v over its magnitude. It's just radical 3. It just said find a single vector.
Yeah.
Yeah, so this is the vector, right? This is the vector that's orthogonal to both of those. Or its negative would also work. Right, but that's the sort of manipulation you can try sometimes. So if you're looking for a vector, you don't know what it is, just make it an arbitrary vector. Throw it in the right equation to get what you want, and then play around with the equations, right? Other questions?
Yeah.
No.
25. Second edition.
Okay, what does that say?
Find the acute angle between the line, and he give us two equations.
Find the acute angle between
The lines.
the two lines. Okay.
Yep.
Oh, well, the thing is, we did that thing where we could find the vector that gives you the direction of a line. Remember we did it here? Do you remember? We did it in the...
35, you mean?
Yeah.
Oh,
Where you had the general form for a line and you could figure out the vector by doing the slope and rise over run thing.
yeah, but I didn't get how you got the, you get the equation y equals something, right? And you take the slope,
This is what, 25?
yeah, 25.
In the second edition? And you said the lines are?
2x minus y equals 3, and 3x plus y equals 7.
Right, so we can actually find the vector for this, right? These are going to just be two lines in space, right? So I mean, you could draw the picture if you want. But. So how do you draw this picture? Let y equals 0, your x would be 3 over 2. X equals 0, your y would be minus 3. So one line is that.
Yeah, I
X
did
would be
rise
here.
over run for this.
7 over 3, y equals 7. Right, so really they want to find the angle between these two lines, but you can actually find the vector that described the two and then use that formula we had last time with the dot product and cosine theta. So what's the vector that describes this line? Well, if I
So
solve
that
for
would be
y, y would be
1.
2x minus 3.
Yes,
So it's 2 over 1.
Yeah,
So rise over run, right? So rise is 2, run is 1. So
and
I
the
can
other
use that
one is
vector.
negative 3 over 1.
Here I say y is minus 3x plus 7, which I think of negative 3 over 1. So this, I'm moving to the right, so I'll make the run positive, and then this negative 3. So those are my two vectors. So now I know, so let's call these something. That's A, this is B. Well, the acute angle between A and B, how do you find that?
Well, I used the A dot B cosine.
The
Equals?
magnitude of A. Into the magnitude.
Cosine theta.
Right, that's the angle we're after. So let's find them. Theta would be equal to
Cosine inverse.
cosine inverse.
A dot B over absolute A, absolute B.
You can finish that, right? That reminds me, someone asked me yesterday, I think it was Nasifa. Nasifa, that's right. What if the angle is negative? Can the angle be negative from this formula?
Not an absolute, well, you'd have to know what quadrant you're working in to fix it.
Well, if let's say cosine theta, if it's negative, couldn't you find the reference angle that would be within the range, within the domain?
You could, yeah.
So like, for example, if it's like negative pi over 3, that's the same thing as finding the cosine of like 2 pi over 3.
Sure, yeah. No, well, actually. But, yeah, but would you ever even need to worry about reference angles here? Could this ever give you a negative answer?
I don't think this could ever give you a negative answer because you're working in absolute numbers.
Well, A dot B
Absolute
is not absolute. A dot B could be negative.
That's true.
A dot
But-
B is negative on this.
Yeah, you would still have to worry about what reference.
Yeah?
It's negative 5, right?
Yeah, I know you can get something undefined because if you have something larger than 1 or something like that, if whatever, I don't know, probably something like that, if my calculator in the past, it would always give an error message, so.
Right, but that won't happen here.
No,
The way
I'm
we
saying that.
prove this, it won't work. I mean, the only way you could get something undefined is if the magnitude of one of these are 0 and then all bets are off.
No,
Yeah?
it doesn't matter.
Because the triangles are less than 180 degrees and cosine positive between 0 and 1. Everything else is absolute.
You're on the right track. The big hint is the function we're using.
Oh, it's restricted to 2 domains.
Cosine inverse.
Yeah.
Pre-calculus. It only gives you outputs between 0 and pi, which means this will never give you a negative answer. Right? So I sort of brushed it off yesterday. I wanted to see if you guys knew why I brushed it off, but I expected you to remember that. Okay, all right. One more question? Huh? Second edition? Okay, last question. She picked a long one. First edition, number 19. So they gave us 3 points, and they said decide whether the triangle formed by connecting these points is a right-angled triangle. So we're given point P, which is 1 minus 3 minus 2. Q, which is 2, 0, 4, minus 4. R, which is 6 minus 2 minus 5. And the question is triangle PQR right triangle? Right angle? So let's start by drawing a picture. That's always nice. That's what you're going to find that it is very often true in calculus 3. Drawing a picture is going to help you figure things out a lot. It's just that the pictures eventually be a lot more complicated than you're used to. So let's just say this is point P. So this is 1 minus 3 minus 2. This is 2, 0 minus 4. This is 6 minus 2 minus 5. Connect them with the... Okay, how do we figure out if this is actually a right triangle? Yeah.
So first we find the coordinates for the vectors, like PQ,
Right.
QR, and PR.
Find that vector, PQ, then we can find the vector QR, then we can find the vector RP. So let's do that. PQ would be what vector? 2 minus 1,
0 minus minus 3.
0 minus a negative 3.
Negative 4 minus negative 2.
Right? And then if we do QR,
It's 4, negative 2, negative 1.
and if we do RP,
5, 1, negative 3.
5,
1,
1,
negative 3.
negative 3. Okay, so now we have these guys in vectors. Now what do you think?
A dot B.
We
So
find
if you
the
do,
angle between the two vectors.
Yeah. Oh, you're going to want to find the angle between two of these vectors?
Like
Yeah.
first,
I would
say
dot
choose
product them and
You
it
could also
became
try to
zero.
do the dot product and see if that's 0. I mean,
Because it does come to
because
0.
then you don't have to do the cosine inverse.
And
Right?
it-
So you're going to check, is this a right angle? Right? How would you know if that's a right angle? Dot product these two guys. Right? If you don't get 0, it doesn't mean it's not right angle. This might be the right angle, so you check the dot product here. And then, or this might be the right angle, check the dot product there. And you just do 3 dot products, and if you're lucky, you might hit it, or if you're not, you might go through all 3. So then, check if you do RP dot product with PQ, what would you get? 5 plus 3 plus 6, not 0. Okay, so let's go the other way. Let's do it. Check another angle. I can check PQ dot product with QR. That'll give me 4 minus 6 plus 2. What's that?
0.
0. Can stop, don't have to check the other one, that's a right angle. Alright, so today we are going to do a different kind of product of two vectors called the cross product. And you're going to realize that it makes one of our homework problems have a lot less guesswork into it, and it's actually going to be useful far beyond that. Oh, pass out the homework. Pass it to the front. Okay, so let's begin. Cross product, also called the vector product. All right, so remember another name for the dot product with the scalar product. This is a different kind of product. And the nickname for this guy is the vector product, but usually you'll hear it called the cross product. Why? Because it has a cross symbol. I can tell you, mathematicians are really creative when coming up with names for them, right? Notation. Cross product of A with B is denoted A cross B. Just like a cross there. Okay? And here's a very important thing. It is only defined for three-dimensional vectors. Something very important. Its definition is the following. That A be A1, A2, A3, right? Has to be a three-dimensional vector, has three components. B be the vector B1, B2, B3. Then A cross B is defined to be another vector, and here's the vector. A2, B3 minus A3, B2. A3, B1 minus A1, B3. A1, B2 minus A2, B1. Which is like super intuitive. Right? Obviously, why not? Why wouldn't you define a product that way? Right? This monstrosity is called the cross product, and yes, I want you to memorize it. So.
Can you repeat it? I can't really see it.
Oh, A2B3 minus A3B2.
Slow down.
Can you just do the matrix?
Matrix, yes, that's what I was good enough. You don't have to actually memorize it, because there's a mnemonic for it.
Oh.
And the mnemonic takes us back to algebra, finding the determinant of a 3x3 matrix. Turns out that A cross B is equal to you line the A components in the second row, the B components in the third row. And you find the determinant of this matrix. Who remembers how to find the determinant of a 3x3?
I don't, and I don't expect you to teach a whole thing on it. This was very unhelpful to me because I never learned about this in algebra.
The matrix?
No, No.
Well, at City College they do it in Math 190, but sure, I'll tell you the definition now if you've never seen it before. And if you're going to do 392, you're going to be doing determinants of all sorts of size matrices. So here's the thing. They do the matrix by Laplacian expansion, as it's called. You don't really know what to do that. What they say is they expand along the first row, right? So you look at this first row, right? There's going to be a checkerboard pattern of signs in the background, right? Starting with the top left is a plus, always a plus.
Okay.
Signs alternate afterwards, right? So it's a plus, then a minus, then a plus, and etc. Right? Now what you're going to do is you're going to take the first row, you're going to expand along that row, meaning each element that's here in that row, you're going to write it down first, right? So there's a plus I, that's where the sign comes from. And what's going to happen is you block out everything in the I column and the J column.
Okay.
In its row and column, and you get another matrix, a smaller one.
Okay.
You write that down. So you block that out.
Right.
You have A2, A3, B2, B3. Right? You see that? So you start with the I, it takes a plus sign. Block out everything in that row and column.
Then
You get another smaller box, write that box down.
Okay. I
Right?
can get that.
Now you move on to the J, right? That takes a negative sign. So it's minus J. And by the way, the IJK here is the I hat, J hat. Right. And you do exactly the same thing. Take out everything in that row and column. See the remaining box? You're going to write that down. A1, A3, B1, B3. Finally, plus for the K. You're going to do exactly the same thing. Block out everything in that row and column. You're going to have that box left. You write that down. A1, A2, B1, B2. Right. So if you have a 3 by 3 matrix, as it's called, right, because there are 3 rows, 3 columns, right, you can choose any row or column to expand along. Here, we just always expand along the first row because it's just easier to remember that way. Right, plus sign here, minus sign there, plus sign here. Take each element, block out its row and column, and rewrite the smaller matrix there. Right? So you do it for the I, A2, A3, B2, B3, then you do it for the J, A1, A3, B1, B3, then you do it for the K, A1, A2, B1, B2. Right? You write down those boxes. Now when you end up with this box, that takes on another formula, which is a cross multiplication. Multiply this by that, A2, B3, minus multiply the other way. Right?
Okay.
Multiply it along the main diagonal, subtract multiplying along the other diagonal.
So the notation sort of represents the
Right.
what you're doing.
Minus J. Do the same thing, this times this. A1, B3, minus this times that. B3, B1. Plus K. A1, B2, multiply this by that. Minus, multiply this way. A2, B1. You'll notice you get a vector in IJK notation, which you could, if you like, write it in this notation. It's going to be equivalent. A2, B3, minus A3, B2, comma, negative of this, so I can switch them. A3, B1, minus A1, B3, comma. Come again?
Where you're switching the signs, so it's.
Yeah, because the negative sign was up here. So I made this one negative, and that one
Oh, you
positive.
switched them, I see it.
Plus A1, B2, minus A2, B1, which is this guy. Okay, that's a mnemonic to memorize the cross product. Let's actually do an example. So you guys can see it in action. Let's say my A is the vector 1, 2, 3. My B is the vector 3, 0, 2. Find A cross B. I'll even help you out. I'll set it up for you. A cross B equals I, J, K. Put the A across the first row. 1, 2, 3. Put the B across the second row, and then the third row. 3, 0, 2. We're going to use that to find the matrix. 4, 1, 2, 0. What do you think the answer? You're going to tell me the final answer? What's your final answer? Yeah, tell me the little answer. I want you guys to try it on your own.
I get 4, 7, minus 6.
You got 4, 7, and minus 6. That's your vector? Did everyone get that?
I got 4 minus 7 and 7, negative 5.
4 minus, that's totally different.
Oh, wait. What is that? 4 minus
4, 7.
I got a second. Yeah, this one.
Okay, several people seem to be getting this one. Let's see. Okay, so remember this guy takes the plus sign, right? So whatever number you get by doing that minute calculation, you're just going to put that number here. Take out everything in that row and column. You get this, and you're going to multiply it. 2 by 2 minus 3 times 0, right? That's 4 minus 0. Okay. Now the J takes on the negative sign. So whatever number you get from this, you're going to take the negative of it and put it here. Take out everything in that column and that row. Now you're going to do the computations there. 1 times 2 minus 3 times 3, right? So this is 2 minus 9, and then you take the negative of it, right? So 2 minus 9 is minus 7. You take the negative of that, you get a positive 7. Okay, now we move on to the K. Take out everything in that column and that row. Now we have 1 times 0, 0, minus 2 times 3, which is negative 6. Right? And that takes on a plus sign, so you don't change the sign. So yes, 4, 7, negative 6 is the cross product of that. Okay. So that seems like a fun game, but of course, it's a mathematical definition. It has to be useful somehow, right? Why would you do all that if it wasn't useful? I'll give you a hint as to what the use is. Try these. Take A cross B, dot product it with the vector A. What do you get?
Zero.
Yeah. I want you to take A cross B, dot product with A, and I also want you to take A cross B, dot product it with B.
You get zeros. You have to get zero.
What is
because
this? This
it's
is
orthogonal.
4, 7, minus 6, dot product with the A, 1, 2, 3. So this gives you 4 plus 14, 3 6 is 18. That's 0. It's interesting.
Isn't the cross product always orthogonal?
Minus 6, dot product with the B. How do you know that? 4 times 3, 12 plus 0 minus 12, 0. Oh.
Okay.
What does that tell you? Here, A cross B is orthogonal to not one, but both of them. So remember in the homework just now, we had the question where find the vector that's orthogonal to two given vectors. And we went through and we did our trial and error thing, right? Put a general vector and sort of set up these simultaneous equations and try to solve it. Turns out that if we were given these two vectors and we did that, we would end up with this guy. And guess what? It's not a coincidence. You can prove in general that this will always be the case. If you take a vector that looks like this form and then dot product with this, you'll always get 0. If you dot product with that, you will always get 0. Right? And I'm not going to show you the proof. It's just a direct computation. Just dot this with that, and then dot this with that. You'll always get 0 as the result. So the cross product, yeah, it's not very intuitive, but it's actually super useful. It gives us a way to find a vector that's orthogonal to two other given vectors at the same time. This vector is perpendicular to both of these guys. Right? Super cool, right? No trial and error, you just do this computation. Throw in that matrix, do your little game with the numbers. You get a vector that's orthogonal to both of the vectors in the original product.
Doesn't that mean A and B are parallel?
No, it doesn't. You're thinking in 2D. We're in 3D now. You need to expand your mind. Right? If we were in 2D, it would be the case that they had to be parallel. But nope, we're in 3D, so they don't have to be parallel. Right? I don't know how much this is going to show up. These are two random vectors, right? I can stick angle to angle. They're not parallel, but guess what? My pencil is perpendicular to both of them. Right? in two dimensions, that can't happen, but in 3 dimensions, it can. Right? They don't have to be parallel, but I can still find something that's perpendicular to both. I can find it going in this direction, or I can find it going in that direction.
Although
Right?
the axes, the XYZ axis,
What about them?
yeah, they're all orthogonal to each other.
Yes. So the z-axis is orthogonal to both the x and y-axis,
Right.
and x, and you can reiterate that. Yeah. So in 3 dimensions, this can happen, right? So it doesn't mean they're parallel. They can be whatever they want, but whatever they are, the cross product will give you a vector that's orthogonal to both. So that's the use of this crazy definition. And like I said, it's not a coincidence. You can actually prove it. I'll just state the theorem. Very important fact. We're going to be using that all the time. Moreover, A cross B follows the so-called right-hand rule. By that, I mean your right hand sticking up like that. The idea is, if you point your hand in the direction of the vector A and curl your fingers towards the direction of the vector B with your right hand, your thumb actually tells you the direction that A cross B goes into. right? So if this is A, that's B, your A cross B would be here. It's going to be perpendicular to both of these, but that way, right? And if this was the B and this was the A, in order to curl your hands to in A and curl it to B, you'd have to sort of turn your right hand upside down. And so the cross part would go down. Right. So in other words, let's say A and B are in the same plane on the blackboard. In this case, A cross B would be pointing straight out of the board, right? Because you right hand here, curl here, stick your thumb up, it's pointing out to you, right? If I had my B here, A here, then to stick it in the direction of A, curl towards B, my thumb would have to stick into the board. In this case, A cross B is going in that direction. Right? So it follows the right hand rule, and it's also always, the A cross B is always orthogonal to both vectors in the product. So that's pretty cool. So if you ever need to find a vector that's orthogonal to both, and believe me, there are going to be many times when you do need to find that, you can use a cross product. Yes?
Does this have anything to do with the planes? Like finding a function of a plane or anything like that?
No, it's more elementary. It's strictly a property of vectors.
Because it sounds like the vectors are always on the same plane. No?
Oh, I see where you're getting at. Well, the answer is yes. So later on, I mean, when we get to, what is that, 10.5? Is it 10.5? Yeah, I think it's the next section, 10.5. When you're going to have a plane in space, then yes, it will be true that if you have any two vectors in there, there's going to be a so-called normal vector, which we're going to talk about later. And you can actually find that by using cross products. Yeah, that's where we're headed. But the cross product exists without even thinking about planes. It's just something that we can apply it to planes. So it's just a really cool application. But it's not developed through thinking about planes. There's another important theorem. Remember we had that theorem about the dot product with the angle between the vectors? What was that equation?
Magnitude to the A, B cosine theta. You mean that one?
What? A dot B is equal to?
The
Magnitude of A times magnitude of B times cosine theta.
Right. There's a very similar theorem with the cross product.
They use sine.
It uses sine. You take the magnitude of A cross B, it's actually equal to A, B, sine theta, where theta is the angle between A and B. This gives us a very important fact. Now remember last time we did the one for the dot product, right? A dot B is A magnitude B cosine theta, and we're like, okay, well if we pick the theta to be 90 degrees, meaning perpendicular, we could actually get 0 here. Right? And so two vectors are perpendicular if the dot product was 0. What are the angles that would make sine 0? Right. If theta equals 0 or pi or 2 pi, etc., then sine theta equals 0. But what does that mean for the vectors A and B?
They have to be parallel.
They'd have to be parallel. If the angle between A and B are any of these, they are parallel. Right? So if it's 0, they're parallel and they move in the same direction. If it's pi, they're parallel, but they move in opposite direction. But they're still parallel. They're along the same line. This means A and B are parallel if A cross B equals 0. What's wrong with what I just wrote down?
You wrote 0 without the little vectors.
Okay. That's right, 0 vector, right? A cross B is a vector. And recall, A and B are orthogonal if A dot B equals 0 without the vector sign, because that's a scalar, right? So these are two very important things about our products, right? If the dot product is 0, your vectors are orthogonal. If the cross product is 0, they're parallel, right? And it's always nice to know if two things are perpendicular or parallel, right? You can use the dot product to talk about orthogonal. You can use the cross product to talk about parallel, right?
Could you also get the parallelism from the dot product as well, if it's one or negative one?
Sure, but that doesn't give you much information about, because I mean, in that case, you would just have A dot B would actually be equal to the magnitude of A times the magnitude of B, right? If you're talking about, because if the angle is 0, cosine just gives you 1.
Right, oh, okay, I see, okay.
Right? So then in that case, A dot B is just equal to magnitude of A times magnitude of B, which is really nice, but I don't see how that's really useful.
Yeah, okay, I was hoping that it was.
Okay. Right? But these are two important things about the products that we've talked about so far. So you might think they have word definitions, but they're actually quite useful. And this should be, you can actually prove it goes both ways. It's an if and only if, meaning if you know they're parallel, then it automatically means their cross product is the 0 vector. And if you know the cross product is the 0 vector, it automatically means they're parallel. And yeah. Let's see. Oh, well, that's true. I didn't do the proof for that, but it's not that bad. Here's something that sort of going back to what Carolus was saying. Example. Find a vector orthogonal to the plane that passes through these 3 points. 2, 0, minus 3, 3, 1, 0, 5, 2, 2. I believe this is actually a problem from the first edition. I think that was problem 28 from the first edition. Okay, let's do that. We have 3 points in space. We make a plane that goes through all 3 points. So there's this plane in space. There are 3 points in that plane. There's the point P, which is 2, 0, minus 3. There's the point Q, which is 3, 1, 0. There's the point R, which is 5, 2, 2. My goal is to find some vector that's perpendicular, orthogonal, to this plane. How do I do it? Find 2 vectors that are actually in the plane. And how do I do that? Connecting the points, right? Say we could, connecting any 2 pairs of points will do, but let's say I want to connect P to Q, and then I can connect P to R, right? So those would be 2 vectors that are in the plane, parallel to the plane, and all I need to do now is find a vector that's perpendicular to both of those at the same time. How do I do that? Cross product. So let's actually do that. So here I take PQ and I take PR. PQ would be what?
1, 1, 3.
1, 1, 3. PR would be what?
5.
So we need a vector orthogonal to both of these. Because if you are, you're orthogonal to the plane. So. And the cross product will work. So how do we find the cross product? Well, you do that IJK thing. 1, 1, 3, 3, 2, 5. Going to find the vector here. So what's the vector going to be?
-1, 4,
-1. How do we get -1? The I, everything in that column and row, you block it out. You get a rectangular array of numbers here. This times this minus this times that. So that's 5 minus 6 is -1. For the second coordinate, you block out everything in the J and column and row. This is 5 minus 9.
-5.
So it's what?
It's J. So it's
Yeah,
negative.
so that's 5 minus 9.
Negative.
Yeah.
Right? So that gives you -4, but remember in the J you switch the sign, so it becomes +4. Right? The middle one you always switch the sign. For the last component, you block out everything in that column and row.
2 minus
2 minus 3.
-1.
So that's our vector. Yes.
I'm just wondering if it makes any difference if we do 2 vectors that are tail as opposed to tail.
Makes no difference. Right. Yeah.
Does the formula that you wrote out originally not reflect the negative for J? Like that you put the sign there? Is that using that formula?
You mean the general form that I wrote here in the first? Yeah, it accounts for the sign. Yeah. I mean, hopefully you copied it down right, but yes, it accounts for the sign. Okay. How are we doing? Are we fatigued? Are we okay? You want a break? We can do a 10-minute break, and then we can come back. There are more useful facts about the cross product. How do you know 2 vectors are perpendicular? I know if they're parallel. I find a vector that's perpendicular to 2 other vectors. All right. Next time I ask you those questions, right away. Right away. Okay. All right. There are some other useful things about the cross product. Let me show you one of them. Let's say we had a parallelogram. And let's say let's take the parallelogram spanned by two vectors, right? Which is sort of the deal here. Anyone remember how you find the area of a parallelogram?
Based on side.
Hmm?
Based on side.
Base times height, yes. You remember how that was developed? It's sort of like cut it in two triangles, but they actually use right triangles and then pieced them together, right? If I cut the right triangle there, what's the height going to be? B sine whatever that theta is, right? So, area in this case would be height times base, base times height, doesn't matter. Height times base, right? But what is the height? We already know, it's b sine theta. And what is the base?
Magnitude of A.
Magnitude of A. Of course, as multiplication of scalars, we can rearrange this. And what's that? That's actually the magnitude of the cross product. So by taking the magnitude of the cross product, it has the geometric interpretation of being the area of the parallelogram spanned by the two vectors. That's another useful thing you can use the cross product for. If you know a parallelogram is spanned by two vectors, you can actually find the area of the parallelogram by just taking their cross product and finding the magnitude. Or if we have the area of a triangle. Theta. Triangle, let's call this A, let's call that B. You guys remember there's a formula that says the area of a triangle is half AB sine theta? You guys remember that from geometry class? Well, if you didn't, you could actually use this, right? Just think of the triangle as being a parallelogram cut in half. Right? Half of the parallelogram. You could think of it that way. But there's actually a formula here, which I think they developed that formula from cutting that in half, right? But that is, again, that's the magnitude of the cross product. So if you have a triangle that's spanned by A and B, the area is just half the magnitude of the cross product. This is the area of triangle. So those are some nice geometrical interpretations. Now we're going to do the properties. Similar to how we did the properties for the dot product, to find out what sort of algebraic properties it possesses. Probably the most important fact right off the bat is that the cross product is actually not commutative, right? The dot product was, but the cross product actually isn't. It turns out that A cross B is actually the negative of B cross A, right? And you can sort of even see this from the right-hand rule, right? So you know if there's some points this way or that way, the vector is actually going in opposite directions. So it's actually not commutative, right? So it actually, if there's a case where it matters how you do the cross product, you have to know which one you should do first. the distributive property still product property still sort of work. So this is one of the reasons why we always write down these properties, although some of them might seem like intuitive, but it's not always intuitive. So for example, here, you hear the word product and you just think, oh, it's commutative, but it's not always the case. Right? So that's why we have to always check these things, that they actually work. The distributive property, thank goodness, actually works. And again, the order in which you multiply matters, right? So the positions actually matter. This is how the dot product and the cross product mingle with each other. You can actually switch them. Here's a word formula. You don't find use for it very often, but you might. These are scalar multiples here, because these are scalars. Something called a scalar triple product. It's actually the guy that looks like this. And if A equals A1, A2, A3, B equals A1, A2, A3, C equals C1, C2, C3, then scalar is that guy, which is the same matrix thing. And so you can actually find this guy by doing, expand along the first row. This takes a plus, a minus, a plus, and it's not a vector in this case because there's no ij, so it'll just give you an answer, a scalar answer. And geometrically what this is actually the volume of a parallelogram, parallelepiped, I think it's called. By that I mean hyphen. Right? Meaning if you have vectors that span each the length, the base, and the skewed length, the slant length of a of three-dimensional parallelogram, that actually gives you the volume, right? That computation over there. So I don't think I actually did an example. That's fine. Just wanted to mention it.
What does coplanar mean?
They lie in the same plane. Lie, lay. This PhD in English.
Can I have fries with that?
Right. So yeah, the volume is 0. It means that this vector is actually slapped down in the same plane as the other two. And so the volume is 0. They all lie in the same plane. So if you do that scalar triple product thing, you get 0 as the answer. The geometric interpretation is the three vectors in your triple product, they're all in the same plane. And I believe that's all I wanted to cover for 10.4. So homework for that is due on Monday, which is the next class. And now we're going to move on to 10.5, equations of lines and planes.
I have a question before we go on.
Yes.
Do we have MATLAB homework due for Monday?
No, we didn't do anything.
Okay.
Wait for you guys to copy that down, and we're going to move on. How do you know two vectors are orthogonal?
Because 0.
It's still taking too long. So now we're going to do the equations of lines and planes in 3 dimensions because they actually look quite different from how they look in 2 dimensions, which we're used to. How do you find a vector orthogonal to 2 other vectors? You're not listening fast enough either. Like you're not responding fast enough, not listening fast enough. I know 2 vectors are parallel. All right, let's talk about lines in 2D. Tell me about lines in 2D. What's the equation of a line in 2D?
Y equals mx plus a.
Y equals mx. That's good. Okay, tell me about that equation. Everything you know about that equation.
Ax plus by plus c equals...
What's the m?
Slope.
M is the slope, right? How do I find it?
Rise over run.
Huh?
Rise over run.
Right, it's the delta y over delta x, right, which you could find it if you're given 2 points, you know, like y2 minus y1 over x2 minus x1. Right, what's the b? Y-intercept, right? That's the y value when x is 0. Okay, can you tell me another form of the equation of a line? This is called the slope-intercept form of the equation of a line. Right, there's also something called the point slope form of the equation of the line. What's that?
Y minus y1 x times x minus x1.
Okay, m is the same old slope. What's x1, y1 here?
2 points.
2 points.
That's 1 point. That's a 1
Well,
coordinate.
it's a different point than yx.
Like 2 different points in the line.
We're gonna have to-
It's just a point on the line, right? XY is sort of your general point. It's the point that can vary depending on what you want to solve for, right? So it's a points on the line. Okay, can you tell me another way to describe a line? Another form? Here's the so-called standard form of the equation of a line. What's that?
Equals 0.
Okay. And I mean, from this one you have to, I don't know why it's the standard one, because that one you have to do the most work to actually tell anything about the line. Right, here you can see right away, the slope is this and the point is that. Right, or the slope is that, the y-intercept is that. This one you don't want to say anything about the line, you have to like solve for it. Okay. So there are 3 forms for the equation of a line, and you know the formula, and you can even tell me what all the pieces mean. Right? That's the level of understanding I'm going to need you to have with what I'm about to tell you now. Okay? It turns out that things that look like this are actually planes in 3 dimensions. They're not lines. Right? The equation of lines look very different. But just like with the equations in 2D, they're going to have various formulas. I'm going to talk about 3 formulas for the equation of a line, I think. Was it 3? Yeah, 3. And I need you to know what they are and what all the pieces mean and how to manipulate them to find them, right? So this we all know already. Okay, good. Now we're going to do in 3D or higher. What does a line look like in 3 dimensions?
It's a flat thing.
One. This is called the vector form of the equation. A line. And it is this. R, which is a function of t, is equal to R0 plus t times the vector e. Here, R of t is the line. It's sort of like your y, right? Your y of x is now R of t. It's called a vector form. And R0 is a point the line passes through. T is a parameter. Right, parameter is just something that you guys, yes?
By R naught is a point, you mean R naught is the location vector of the
It's a position vector.
position
Yeah.
vector?
I'm going to show you where this comes from. T is a parameter, and V is the direction vector for the line. Is a vector parallel to the line. And sort of show you where this comes from. So it's sort of equivalent to your point slope form. The V sort of tells you, it's sort of like your slope. It's that guy who tells you what direction the line is going in, right? T is a parameter, so as T varies, you can vary the points on your line. You can run up and down it. R0 is just a single point on the line, right? Which we're thinking of it as a position vector. So we're in 3 dimensions here. There's a random line going on. The random x, y, z coordinate is given by a position vector that goes to here. It gives you the general point. All right, this is your r of t. All right? So this vector traces out all points along this line. So as your t value varies, you get a different point on the line. And this vector tells you how to find it. All right? Just follow the position vector r of t. Now let's say you actually know a constant value, one of a specific point that goes through the line, that's going to be your R0, which we also look at as a position vector. This, we can have a vector that goes in the direction of the line, which we can call it, I don't know, for now we'll call it A. So now, how would we actually find the equation of that? How can I find R in terms of the 2 other vectors I just mentioned?
Are they all the same point of origin?
Yeah, I'm thinking of everyone as a position vector. You can add them, right? Think of A as the vector that goes between this point and that point, right? If you take this plus that, you get the R, right? So R is just equal to R0 plus A. But A can be scaled, right? I can just think of it as some constant times this general vector V that gives me the direction. So that's sort of the idea that they used, right? And one thing you're going to realize here is that the number of parameters you have actually tells you the dimensions of the object that you're looking at, right? So here for a line, you only have 1 parameter. Only t is a parameter, right? If you were talking about planes, you'd have 2 parameters. If you're talking about solid objects, there'd be 3 parameters, and so on and so forth. But this is sort of how we think of a line in 3 dimensions. It's just something that has a parameter t that has that vector equation.
Where's V in that?
Huh?
Where's V in that?
A is just parallel to the vector V. V is just the general. V is just a vector in that general direction. Okay, so I can actually rewrite this. I think. See. R is just the general point x, y, z that traces out this line. R0 is just a particular point, x naught, y naught, z naught. If I say V is a random vector that is given by ABC, then we can also write the vector form as x, y, z equals x0, y0, z0 plus t times ABC. And this is sort of taking you back to Calc 2 when you discuss parametric equations. What do you know about each of the components here? What do they look like?
Line.
X, Y, and Z are the points on the line.
Yeah.
Right.
X naught, Y naught, Z naught is a particular point. So these are actually constants here. ABC is also a particular vector. Those are also constants. So what does this remind you?
Little lines.
Little lines. Right. Mx plus b. Each component looks linear, right? Which means if you have the equation of a line, you need a vector equation where each component is linear. I put a square on the t, it's not a line anymore, right? It has to be linear, right? So that's one way to check. A line is just something where each component is linear, and if you give me a bunch of specific points, I can actually tell you specifically what the components are. But each component has to be linear. So so it's the equation of a line, all the components are linear. I don't know how to get you to remember that. I remember when I was teaching 392 and I was trying to see how much of their Calc 3 they remember, so I was testing them, you know, is this a line, is this a line? And I put all sorts of things in here like exponentials and radicals and cubes, and they're like, is that a line? It could be. No, each component has to be linear for it to be a line, right? Remember that. That's called the vector form for the equation of a line, right? Which, by the way, this tells you what you need. So remember over here when you gave me the formula for the equation of a line, you told me that m was the slope, b was the y-intercept. Or the point-slope form, it means if you have the slope and a point, you can find the equation, right? It tells you what, the formula itself tells you what you need to find the equation. You need two things to find the equation of a line. What are they?
Slope. And a point.
In the language of 3 dimensions. You need a direction vector. I'll put that as D. Right? That gives the direction of the line. Yeah, that's sort of analogous to your slope, but we won't call it slope. It's a vector, it's a direction, right? And the first thing is a point that the line passes through, right? If you tell me those two pieces of information, I can actually write down the equation of a line, right? All I need is a point the line passes through and the direction in which the line is going. Once I have those two things, I can tell you the equation. Right? Just like in the point-slope form. Tell me the slope and a point, I can give you the equation. In 3 dimensions, tell me a point and a direction, I can give you the equation. Right? That's super important, remember that. So it's these essential tidbits of information that really helps you in solving problems, because eventually we're going to tackle problems where we're dealing with planes and lines all over the place, right? So you're going to be able to focus. Know when you're focusing on a line, know what you need. When you're focusing on the plane, know what you need, because they're all going to be mashed into the same problem. So it's really important that you have it solid. Okay, I'm looking for a line, what do I need? Or I'm looking for a plane, what do I need, right? It's very important that you know that. For a line, this is what you need. A point and a direction. You have that, you have everything, okay? And once you have those guys, all you do is you plug them into this equation in this map, right? So the direction, the components of that are actually the coefficients of the t. Notice that, right? They're the coefficients of the variable, right? A point the line passes through is just a constant term, right? They're like your y-intercept, the initial point, right? So know that. But from the vector form, we see that I can actually isolate what the x is, right? I'm saying these two vectors are equal, right? Which means the components have to be equal, right? So x, I can isolate that and say x is x naught plus at. My y value is actually y naught plus bt. My z value is actually z naught plus ct, right? I can actually isolate the components one at a time, right? So if my x behaves like a straight line, like a mx plus b, and my y behaves like a straight line, an mx plus b, and my z behaves like a straight line, then overall I have a straight line, right? So I can actually isolate the factors, right? This is the parametric form. Since each of these are called parametric equations because they're equations in terms of a parameter. That's called the parametric form. So we already have two forms for our line. There's the vector form, and there's the parametric form. Right? So the vector form comes from knowing that you need a point and a direction. You can throw them into a vector. When you isolate each component, you get you get a bunch of equations that you call the parametric form for the equation of a line. And that's not the only form. Where's my eraser? Those aren't the only two forms. You can go one more and eliminate the parameter, right? Let's say we don't want to talk about the line in terms of the parameter. Okay, so in the first equation I can solve for t. I get t would be x minus x0 over a. Also, t would be y minus y0 over b. In the third equation, t would be z minus z0 over c. But if t is equal to each of those, then they're all equal to each other. So I can just write this. That's another form for the equation of a line. This is called the symmetric form. So 3 ways to write down the equation of a line. Just as in 2D we had a bunch of ways, so it shouldn't be surprising we have a bunch of ways in 3 dimensions. There's the vector form, looks like this. So if you know a point it passes through, you put it here, here, here. Know a direction, you put the coefficients here, here, here. You get the vector form. Isolate each component, you get the parametric form. Eliminate the parameter by solving for it and setting each of those expressions equal to each other, you get what's called the symmetric form. So it's important to know if you're given any one of these forms, you should know what you're looking at is a straight line. Just like if in 2 dimensions, if someone gave you a random equation, you'd be able to tell it's a straight line or not. Right? So any one of these forms, you should be able to tell it's actually a line. Now let's do some examples just to sort of make this all concrete. It's very abstract right now. do those two plus. How do you know if two vectors are parallel? How do you know if they're perpendicular? How do you find a vector perpendicular to two given vectors? How do you find the angle between two vectors? A little better. I'm thinking the first test would probably be Thursday next week.
Is it going to be on all of chapter 10?
Yeah. It's in the syllabus what so it'll be like 10.1 to 10.7.
What do you do with a symmetric form if A, B, or C equals 0?
If A, B, or C equals 0, or I can show you. So you're saying you have x naught plus AT, y naught plus bt, and z, just the z component is just like z naught?
Yeah.
Yeah. In that case, you start the symmetric form with the x's. And then you just put a semicolon and you write z equals z naught.
Okay.
That's the standard way to do it. I guess that's a good question because we never divide by 0. So you have to wonder, if it's 0, what do I do? That's what you do. Yeah, so it'll probably be Thursday. I'll post review problems on my website, and you guys already have the link. I'll let you know when I post the problems for practice. So I'll probably post them over the weekend so you can start working on them. Because we're already in 10.5, so we only have 2 more sections. So I'm figuring we'll finish chapter 10 by like Tuesday. And we'll test you on that around Thursday. It's summer, no time. Everything's really finished up. Yeah. Well, what I'm wondering is how you know two vectors are parallel. How do you know they're perpendicular?
Dot product is 0.
How do you find a vector perpendicular to two other vectors?
Cross products.
Okay, how do you do this problem? You plug it in. Okay. So what do we need to find the equation of a line? A point and a direction. And they actually told us that. Point and a direction. Good. So we don't have to do that much work. We can sort of just plug it into our formulas. So let's talk first about the vector form. We know that x, y, z would be equal to the point plus t times the direction vector. That should look like a V. Right? So the point we're given is, you write as a position vector, 1, 2, 3, plus t times, they gave this direction. So leaving it like that is fine, but you could also just write it in one big vector, 1 minus t, 2, 3 plus 2t. So that would be the vector form. The parametric form. Well, you just isolate each of these guys. Say x equals this, y equals this, z equals that. X equals 1 minus t, y equals 2, z equals 3 plus 2t. And we're done. That's the parametric form. And the symmetric form, try to solve, attempt to solve for t everywhere. So in the first case, t would just be x minus 1 divided by negative 1. You can't really solve for t here, we just have that y equals 2. And here if we solve for t, we get z minus 3 divided by 2. So this gives us the symmetric form. X minus 1 over negative 1 is equal to z minus 3 all over 2, semicolon, y equals 2. And that's the symmetric form for that line. Yes?
Is there a particular reason why we didn't write x as, the first part of symmetric form is just 1 minus x?
No, no.
Like, would it help later on if we're plotting that we know?
No. I mean, if you're given it as 1 minus x, you should know when you should switch it, right? I wrote it in this specific form because you can see right away the point is x, y, z, right? So you know that you'll change the sign on this guy and so on and so forth. It's sort of like asking, you know, if you're in a circle, do you rather write it like this? Right? Do you have to write minus a minus? No, but sometimes you just write it that way so you can just see it right away. So right here I can actually look at this and know the point it passes through. 1, 2, 3, right? And I can also know the vector for the direction, minus 1, 0, 2, right? I can just sort of just look at it right away and see the point and the direction. So that's why I decided to write that. Okay, but here I did not give you a direction, so how are we going to do this one? Yeah?
2 points to find a vector.
It's a revolutionary idea. Why didn't I think of that? Okay, so we have our 2 points here. We know there's a line passing through them. So let's find the vector that connects those 2 points, and that actually gives us the direction of the line. It's a great idea. So what's V here? You can just do final minus initial. That's how you find the vector connecting 2 points, right? So what's that? 2. So now can I find the line?
Yeah, sure, you can just use either one.
Yeah.
Use either one of the points, right. All I need to find the equator line is a point and a direction. I have my direction and I have a couple points to choose from. I picked the first one for no, well, there's a reason, it has a 0 in it. Right? right? But it really doesn't matter which one you pick, right? So I'll pick any point, right? So I'm going to say it's -1 to 0 plus t times this vector. Here, I could have it at a point using 3, 1, 2 is also fine. I just avoided it because this one had a 0 and I figured, 0 is going to be easier to work with computation.
Are you supposed to write it with point in brackets, or?
Yes, because you're thinking of them as vectors. It's a vector equation. Right? So you think of the point as a position vector. You sort of interpret it that way. All right, which I can write the general form here. -1 plus 4t, 2 minus t, and then 2t. They never ask for a specific form, so I figure I'll leave it in the vector form. Say that's my line, and that's part A. Where does that line intersect the xz plane?
When
Yeah?
Y equals 0.
y equals,
T equals 2.
Right. In the xz plane, y equals 0. But I know what my y component is here. 2 minus t equals 0, which means t equals 2. So what point does it intersect the xz plane? All right, you just plug in the point t equals 2, because that's the point where the y coordinate will give you 0. -1 plus, well, I can look at it as a point now. 4t plus 4 times t, which is 2, comma,
Y is
0, comma,
2 times 2.
2 times 2. So that point is 8 minus 1, 7, 0, 4. So that's the point it will intersect the xz plane. What point would it intersect that surface? By the way, that surface is actually a plane. We're going to talk about the equation of a plane. Not today, but soon. Monday. How do I know where it will intersect that plane? If you what? Cross what with what?
If it's,
Cos pi equals 0.
Well, cross product equals 0 just means parallel. It doesn't mean necessarily intersecting.
Could we find out? Could we find out where each plane it lies on? I mean, on the x, y, and on the z plane.
No, I want to know where the line intersects that plane. X plus 2y minus 3z equals 5.
Plug in the coordinates.
How about you plug them in, right? So in the line, x is actually equal to minus 1 plus 4t. Y is actually equal to 2 minus t, and z is actually equal to 2t. if you're going to intersect something, what do? You set the coordinates equal to each other. So the x here must be the x in the plane. Plug these in the plane. It's actually a plane. I called it surface here because I wanted to like maintain the suspense. So you're like, oh, what's that surface? It's actually a plane. So you would have x, which I know here is minus 1 plus 4t, plus 2 times y, plus 2 times 2 minus t, minus 3 times the z, which I know is going to be 2t, and that should give me 5. So now what I can do, I can solve for t. Once I have t, I can plug it back into my equation of a line to find the point it passes through. So this would give me what? This is 4t minus 2. Should I just write it down? Okay, so we have 4t minus 2t, that's 2t minus 6t, that's minus 4t. So this is
6 minus 4 is 2. So negative 4t equals 2. Negative 1.
equals 2.
And then you have 2 equals negative 1.
Right, so now we plug this in.
Ron, do you have another battery?
No, I have an extension cord if you need to plug the thing in there.
Probably do.
How much more time do we have?
2 minutes.
What?
2 minutes.
No, not for the class. No, for the class, I don't know how much time I say we have. Say it when I say so. Come on, the camera.
The camera's dying
Come
now.
on, camera.
I tried, guys. I tried, guys.
Well, I actually don't. Let's just hurry up and finish this and then we go. Since technically it's time for the class, whatever. Okay, so x is equal to minus 1 plus 4 times, there's minus 1 plus 4t, right? Minus a half. Y was equal to 2 minus a half. And z was equal to 2 times minus a half, right?
Right.
So that's minus 1, minus 2. Two plus a half is what? 5 over 3. And z would be minus 1. So the point is minus 3, 5 over 2, minus 2. And I guess we'll stop there. So we haven't finished 10.5, so the homework for that isn't due, but of course I'm going to quiz you on everything we've done before. So, huh?
Monday.
On Monday, yeah, there's a quiz on Monday. How do we know two vectors are orthogonal?
Oh, please don't.
Someone wakes up in your bed like 3 a.m.